Chemical Kinetics, Part 17, Catalysts. There are three factors that affect reaction rate. The first has to do with the physical state of the reactants. If you have solid reactants, increasing surface area increases reaction rate. If you have liquids, increasing concentration increases reaction rate. And if you have gases, increasing pressure increases reaction rate. The second factor has to do with temperature. When you increase the temperature, what's going to happen is we're going to get a higher value for the rate constant, K, and that means that the rate of the reaction will increase. So typically at higher temperatures, reactions happen faster. In this video, we're going to consider the presence of a catalyst and how that can speed up a reaction. Now, it's a common practice in chemistry to speed up some reactions by using a catalyst. And it's also a common practice to slow down other reactions, undesirable reactions like the corrosion of metals, by removing or inhibiting a catalyst. A catalyst is a substance that increases reaction rate or speeds up a reaction, but does not get used up, or in other words, does not undergo a permanent chemical change in the reaction. So how do they work? Well, let's consider that the general rate law for a reaction with two reactants A and B forming products looks like this. The rate of the reaction is equal to K, the rate constant, times the concentration of chemical A to the M power times the concentration of chemical B to the N power. So from that equation, we can see that to increase reaction rate, a catalyst must increase the magnitude of K, the rate constant. Okay, if that's true, let's consider the Arrhenius equation, or at least this version of the Arrhenius equation that tells us how we could calculate K. K is dependent upon the variable A, which is the frequency factor. Now, you might remember that the frequency factor, A, has to do with the frequency of collisions that are occurring, as well as the proper orientation of those collisions. Now, the other factor that affects K is this expression here, the number E to the negative EA over RT, where EA is activation energy, R is the ideal gas constant, 8.314 joules per mole Kelvin, and T is temperature in kelvins. This is an expression of the fraction of molecules that have an energy equal or greater than the activation energy. In other words, an energy necessary for the reaction to occur. So a catalyst can increase the value of K by either increasing A or increasing the activation energy, because R is a constant, and we're assuming that this is at any given temperature T. So increasing the frequency factor, A, occurs by assisting in the proper orientation of molecules. And then the second way that catalysts can affect the value of K is by lowering the activation energy, the EA value. And that happens by providing a new reaction mechanism. In other words, the catalyst changes the mechanism of a reaction to a new mechanism. Now notice that this would be the most dramatic effect because the negative of activation energy is an exponential term in this equation. That means the activation energy exponentially affects the rate constant K. And since it has an exponential effect, it's going to be by far more influential. So we can say as a general rule that a catalyst lowers activation energy. Now that can be a little confusing that we have a negative exponent here, and lowering the value of that negative exponent would make the value of K bigger. So let's just take a look at a quick math review to see that that's true. Let's, for example, consider 10 to the negative 1 power. That's equal by definition to 1 over 10 to the 1 power, or 0.1. 10 to the negative 2 power is 1 over 10 to the second power, and that's 0.01. 10 to the negative 5 is equal to 1 over 10 to the 5, or 0.00001, where the 1 is 5 places to the right of the decimal. we can say that the smaller a negative exponent is, the bigger the magnitude of the overall value. Well, that's important to us then, because the smaller the negative exponent is here, the smaller the activation energy, the bigger the rate constant. And the bigger the rate constant, the bigger the rate, the faster the reaction. So lowering activation energy makes the reaction happen faster. It makes a bigger reaction rate. All right, so let's consider catalysts. There are two types. One is a homogeneous catalyst and the other is a heterogeneous catalyst. Let's consider a homogeneous catalyst first. We can say a catalyst is homogeneous when it has the same phase as the reactants. And this is pretty common when we have reactions that have aqueous substances or reactions with gases. So let's consider this example. We have aqueous H2O2, which is hydrogen peroxide, decomposing to form two H2Os that are liquid, that's two water molecules, and one O2 gaseous molecule, that's gaseous oxygen. Now that's a slow reaction without a catalyst. There are several catalysts that can speed this reaction up. One of them is Br1- ion, or bromide ion. With Br1- as a catalyst, this becomes a two-step reaction mechanism. Now you can't just open a bottle of Br1- from a chemical stockroom. Br1- has to be attached to some positive ion in an ionic compound. So let's add HBr. Let's add hydrobromic acid. Now the hydrogen in this reaction is really just a spectator ion. We could use other types of positive ions combined with Br1- that would also work, as long as they wouldn't have any side reactions going on. So just remember that the hydrogen throughout is a spectator ion. Now the first step in this multi-step mechanism that is going to happen with the Br1- catalyst is that two bromide ions react with H2O2, hydrogen peroxide, and then there's those two hydrogen ions there. And what happens is we're going to get a Br2 molecule, that's bromine, right? Diatomic bromine. And we're going to get two water molecules. The second step is that the Br2, the diatomic bromine molecule, reacts with another hydrogen peroxide, H2O2, and forms two Br1-. Well, hey, there it is. That's the catalyst that we started with, and here it is produced at the end. So while it did take part in the reaction forming this intermediate, the intermediate broke apart again and reformed the catalyst. The hydrogen ions are here as spectators. And in the second step, we also produce some O2 gas. If we add up the two steps of this reaction, you can verify that it would add up to be, it would simplify down to be this reaction up here, the overall reaction. Now notice that we have Br2 as an intermediate. So how can you tell the difference between a catalyst, Br1-, and an intermediate, Br2? We can say that a catalyst, in this case Br1-, but always a catalyst will be present at the start of the reaction. And an intermediate, in this case Br2, but always the intermediate will be formed during the reaction and then reacted away before the reaction's over. Now if we want to symbolize a catalyst in a chemical equation, what we do is we put the catalyst above the arrow like this. So if there's nothing above the arrow, this would represent an uncatalyzed reaction, and again that would be slow. And if we have that above the arrow, that's a catalyzed reaction, and we could expect that to be a faster reaction. Let's take a look at an energy diagram. Now you could call this a reaction diagram or an energy profile, or some people would call it a potential energy diagram for that same reaction. Here we have the uncatalyzed reaction. It's kind of in darker script here, in bold script. And I'm going to map that out as the reaction progresses with potential energy on the y-axis with this bold dashed line. So we start with the reactants, in this case just two H2O2 molecules. We break the bonds involved get to this transition state up here where the bonds are broken, and then the bonds reform and form two H2Os and O2. Now let's consider the catalyzed reaction. This is in lighter script, and I'm going to symbolize it on the graph with this lighter dotted line. Notice that we have Br1 minus written as a catalyst. Now this is a two-step reaction mechanism. In the first step, the H2O2 combines with Br1 minus, and then remember that two H1 pluses are spectators. Br2 plus, or rather Br2 molecule, is formed, and two H2O molecules are formed. Then in the second step, so we went through the first step already, right? The Br2 would be present here. That's where the intermediate is at the dip in multi-step reaction. So the Br2 combines with some more H2O2, reforms the catalyst, two Br1 minuses, and then there's our spectator ion. And notice the spectator ion's not doing anything in the reaction at all. And then it also forms O2. So with the presence of the catalyst, we start with these chemicals. And remember that we would introduce these as hydrobromic acid, HBr. And we end up with these chemicals. The hydrogens are spectator ions because they could be substituted. And the Br1 minus, or bromide ion, is the catalyst. Step 1 occurs here. Step 2 occurs here. Now the activation energy for the uncatalyzed reaction would be the difference between the energy of the reactants and the top of that peak. The activation energy for step 1 would be the difference between the energy of the reactants and the top of that peak. And the activation energy for step 2 would be the difference between this part right here and the top of that peak. Notice that each step in a catalyzed reaction mechanism must have lower activation energy than the uncatalyzed reaction mechanism, and pretty much substantially lower. Otherwise, it won't really speed the reaction up. So we're going to see that this activation energy and this activation energy are substantially smaller than this activation energy. Also notice that the catalyst does not change the potential energy of the reactants or the products. Well, that means the overall change in energy for the reaction does not change. In other words, between a catalyzed and uncatalyzed reaction, the delta E value stays the same. And you could say the same thing for the delta H, or the enthalpy. So notice that the reactants start and end at the same position for both the uncatalyzed reaction and the catalyzed reaction. So the delta E between these two positions, or you could even say the delta H between those two positions, the change in enthalpy, is unaffected by the presence of a catalyst. All the catalyst is doing is making the activation energy smaller. Now, it doesn't always have to involve a multi-step process. Sometimes it just changes the activation energy and keeps the reaction as a single-step process. All right, let's consider a heterogeneous catalyst now. A heterogeneous catalyst is a catalyst that has a different phase than the reactants. Now, this is common where we have a solid catalyst in gaseous or aqueous reactions. A common way to see a heterogeneous catalyst is with a surface catalyst. This is where we have a solid that is configured to have a high surface area. In other words, a solid as a powder, or a solid that has several different surfaces, maybe like an array of tubes through which the reaction will pass. And the surface of each tube provides a catalyst. So there's lots of different ways that we can have a high surface area. Now, if you consider that a solid is going to have molecules on the interior and molecules at the surface, we can say that molecules at the surface of a solid will have unused bonding capacity. In other words, they will have some attraction that's not being used up compared to molecules that are in the interior of the solid where they're surrounded by other molecules. So surfaces of solids can be very reactive because of that unused bonding capacity for the surface. Now, before we go any further, let's get a few definitions clear. This is kind of a new term here. It's adsorption. Adsorption refers to the binding of molecules onto a surface. Now, you're probably familiar with the second term, absorption. Absorption, with a B, is when the molecules go into the interior of a substance or interior of a material. So if you have a sponge and you soak up some water, we could say that the sponge is absorbing the water. If I were to take a solid surface like the surface of this marker and put some water on it, we could say that the water is adsorbed to the surface of the marker because it wouldn't soak into the marker, wouldn't soak into the plastic. So adsorption is just sticking to the surface. All right, so let's consider that with surface catalysis. And this is common with metal catalysts. What we're going to see is that reactant molecules adsorb to the surface, so they stick onto a surface. Upon adsorption, some bonds in reactant molecules are broken. Atoms and molecules that are adsorbed to a surface are typically free to move around on that surface. They can migrate across that surface. And when they do that, that allows them to collide with other reactants. So products form when migrating reactant particles collide. And then once the products form, they no longer are adsorbed. So they're released from the surface, and we would say that that's being desorbed. So that's easiest to consider with an example. Let's say that we take a look at this example of a surface catalyst. We have the molecule C2H4, that's a gas, combining with H2, that's a gas. Now consider that if we have gaseous molecules, because they're gases, the particles would be separated by lots of empty space. So what can we do to get the particles to be closer together? One of the things is to introduce a catalyst, and here we're going to use platinum, PT, as our catalyst. Now, this reaction without the catalyst happens relatively slowly, but if we put the catalyst there, it really speeds up. The product is going to be C2H6. So here's how it works. Let's say we have a platinum catalyst here, and at the surface of that catalyst, and we could have a sheet of platinum, we could have some platinum dust. The more surface area for the platinum, the faster this would happen. So let's say we have a surface here. The first thing that's going to happen is the reactants will adsorb to the surface. They're going to get stuck onto the platinum surface. So the H2 and the C2H4 gases will stick to the surface. Now when they stick to the surface, the H2 bonds will break upon adsorption. And they will migrate across that surface. Now it's not much of a stretch to know that metals are characterized by the sea of valence electrons theory. So we can say that valence electrons are loosely held on by metal atoms and they pass relatively easily between metal atoms. Now, as a result of that sea of valence electrons effect, it's easy to consider that molecules or atoms or ions could migrate across the surface. So as the hydrogen atoms are migrating across the surface, bouncing around along that surface, they will bump into some H2, some C2H4. Oops, that's a typo there. It should be H4. Or I guess that's just a writing mistake. So when a hydrogen bounces into or collides with that C2H4, if it has proper orientation and sufficient energy, it'll form C2H5. So first one and then another hydrogen atom will collide with that hydrocarbon. So once the C2H5 gets formed, another hydrogen collides with it and it forms C2H6. C2H6 no longer has any attraction for the surface. So after the product C2H6 forms, it desorbs or detaches from the surface. So this is an example of surface catalysis. It just gives us a spot where the reaction can happen. It kind of brings the reactants together and allows them to congregate together on that surface. Now before we wrap this up with catalysts, let's consider enzymes. Enzymes are biological catalysts. They're typically really big molecules that are proteins. Now, biological catalysts, enzymes, are very much more efficient at speeding up reactions than non-biological catalysts that you'd see in a regular chemical reaction. So enzymes are really, really important for the chemistry of living things. Your body is really just a giant big bag of chemicals where reactions are happening, and some reactions are sped up by the presence of enzymes, and other reactions are slowed down when enzymes are not present. So check out the number of reactions happening here with these biological catalysts. They can be on the order of 10 to the third, or 1,000, to 10 to the seventh, or 10 million reactions per second. That's a lot of reactions per second. Enzymes are very efficient. And the reason they're so efficient is because they have very low activation energy. Reactions have a low activation energy in the presence of enzymes. To understand the very basics of how enzymes work, let's consider what's called the lock and key model. So we have an enzyme here, an enzyme molecule, and there will be a certain part of that molecule that will act as what's called an active site. A substrate is any substance that reacts with an enzyme. So when the enzyme and the substrate line up at that active site, they come together and they stick to each other by intermolecular forces, or van der Waals forces, hydrogen bonding, dipole-dipole attractions, or dispersion forces, depending on the polarity of the enzyme and the polarity of the substrate. When they stick together, we get an enzyme-substrate complex. Now there are several different things that can happen here to facilitate the reaction of that substrate. We're not going to get into all the different ways that enzymes can operate, but what will happen is that after the substrate forms, the enzyme will facilitate the reaction of that substrate, and it will be released as two different products. And the enzyme will be present again to react with another substrate molecule. Now, there are things that are called enzyme inhibitors. They could be toxic metals or nerve poisons or some other type of a toxin. And what they can do is they can clog the active site. So if you get some molecule that's stuck onto the active site of that enzyme that's really not supposed to be there, that can shut that enzyme down. Another thing that an enzyme inhibitor can do is react with a different part of the enzyme to change the structure or change the shape of that active site. And then it will distort the enzyme so it's no longer effective. So studying enzymes is a really, really big deal in biology. And it's something that is a big part of research right now in biochemistry.